All right, guys, in the last video, we were talking about densitometer reads and all of these things about absorbance and what's going on onto the surface of a plate and these little components absorbing UV wavelength, whatever they are, 254, 350, 418, blah, blah, blah. Okay, well, either way, we were talking about absorbance and what goes on in this area or in this world of quantifying TLC images and TLC ideas. Absorbance is only one part of the factor, though, because we can't talk about fluorescence. And fluorescence is something that we could have talked about in spectroscopy as well. We don't do a lot with fluorescence, and that's why sometimes I just leave this little nugget of information out. It seems like very few things can be ran on a fluorimeter, and fluorescence is needed in order for a sample to be analyzed on a fluorimeter, but we also have this option as well on the scanners and on HPTLC. So fluorescence is the idea that things are going to glow. That's what they're going to do. They're going to glow. All right. So this idea is that it's like a glow in the dark type of situation here. And this is great because, you know, sometimes that works. Sometimes it does not, though. And that's fine because some things respond very well to fluorimeters. Some do not. The ones that do, though, are highly sensitive, which is why a fluorimeter is actually so good. Because, you know, the equivalent here is actually what I like to say the fluorescence is all about. Is imagine you being in a completely dark room. Completely dark. I mean, there's nothing in it at all. It is completely closed off. No doors, no windows. I've locked you up and I'm not going to let you out. And then let's say the only thing that you have is a flashlight, and you're going to turn that flashlight on. Okay, so what you're going to see is a very obvious area where the flashlight is going to be turned on. That is fluorescence at its heart. So this idea is that samples are going to glow, and they're going to glow, and we're going to be able to pick them up, and we're going to be able to pick them up much better. So it's extremely more sensitive than absorbance. It operates in a slightly different way. And if we want to talk about the nitty-gritty of fluorescence, it is the idea that these molecules are going to go from ground state to excited state, because that's exactly what goes on with absorbance too at the same time. Then when they go back to our ground state, when they go back home, right, when they settle down, simmer down, have the sugar crash, energy of some form or fashion is going to be given off at a higher wavelength. And that higher wavelength is the glow that we see. Now, again, the objective here is if it can respond to fluorescence, it is way more sensitive. And when I say that, if you look on the screen, it is 100 times more sensitive than something like absorbance can be. So if you want to go small, and if you want to go teeny tiny, and you don't have a lot of sample, or you don't have a lot of that component within the sample, folks, fluorescence is where it's at, because it is extremely sensitive in what it does. Again, it is very easy to see that dark room, to see that flashlight that turns on in a completely dark room. Anyone, it's obvious. So these fluorescence types of methods are, again, very obvious. Now compare that to absorbance, and absorbance is the idea that you've got a room and there's a lot of flashlights that turned on in the room to completely brighten it up. And then let's say that one of those flashlights out of the many turns off. That is absorbance. So it is a molecule that's absorbing light energy, and that absorbance kind of makes that one little area go dark. We can see that. We know there's a change, but this is why fluorescence is very often way more sensitive, because it's just a different type of perspective that we're doing here. Fluorescence is the same way. It operates by the same method in a densitometer read. The light source is going to cut on. You're going to choose the right light source. It's going to go through the monochromator. This picks out 1 nanometer of wavelength. That nanometer of wavelength is going to go on to a sample. Oh, look, there it is. I see it. And then what you're going to get is the original kind of light energy with extra, because it is now glow in the dark. So that extra is going to mean that the detector is going to be able to see it even easier than in absorbance readouts. And if that's something that your compound does, then that's great. This was another representation of our peak profiles that we begin to talk about. And this is just the relationship with the absorbance or whatever type of signal that we are getting from our instrument. And that's going to be on the y-axis. So the y-axis, this says reflectance, but it can just be a signal. That's really how I want you to refer to it as. And then on the x-axis down here at the very bottom, this is just kind of the distance from the point of origin. So very often this distance is going to be in millimeters or in centimeters, depending on how the machine makes its measurement. So migration time is another thing that they like to use here. Instead of the word distance, they have migrated. They have migrated from the point of origin. So how long did it take to get them to where they were going? And we can call that migration time. So migration time is an appropriate unit on the x-axis. But actually, too, it's just really straight up distance. That's what this is. So what we're going to see is that in the beginning, this is like the origination point. This is where it's going to start. And all of my sample components have moved away from the start line and they're traveling up the plate. So as they do, there was nothing here, right? They kept traveling. And then, there's my first component. There's my first circle. There's my first band that's lower on the plate. That's the one that it saw first. And then once it went back down to baseline, then there it went. So there is a second spot or a second band on the plate. And then there we go. There's a third spot or a third sample that is picked up in that lane. So we are talking about the same lane. And in that lane, as of right now, we have already ran across of 3 components that are in that sample that we can visualize, that we can see, that we can image. After that third one, then the plate is pretty barren. There's nothing really here, nothing going on. It's flat. And then finally we get a and then a there again. So I see another spot. I see another band that shows up a little bit later. So again, what's happening on the plate here is that this is my origination line. So that is where I start on the left-hand side of that graph, or densitogram, or a densiogram, whatever they want to call it. So here's the start line, and as it goes up, I see a band that was appropriate here. And then right after that, I see another band. And then right after that, I see another band. And then there was a little bit of distance here. There was nothing going on as it traveled up and up and up that lane. And then it saw something, and there is an additional lane. That was this one, all right? And then it looks like it goes back down the flat line for quite a bit. There's nothing there. And then a huge band that shows up and comes back down. So very, very dark, of course. And that's going to be maybe there. Who knows? But this is how that densitogram is going to be comparable to what's happening on a TLC plate. As we've talked about before, the one on the right-hand side, folks, that is our mobile phase band. Our mobile phases do absorb UV radiation. Very often they do, because we are using things like ethyl acetate and toluene and acetones. Unless they're just straight up alcohols, they're probably not going to show a lot of absorbance at all, or they are going to show absorbance. The alcohols are not going to show up hardly any absorbance. So if it's straight up ethanol, if it's straight up methanol, we probably won't see an absorbance assigned there, but it's still going to show up in some form or fashion, and we still might see a tiny little peak because of contamination. So these things are not going to be super, super clean sometimes. There's going to be impurities that are there, and those impurities can show up on these UV vis spectrums, because that's kind of what they are. It's just in a different perspective. That's all that these densiometry reads are going to be about. All right. So this gives you an example of how that graph really represents information and what it's trying to tell you on the TLC plate. So this is pretty common. It's pretty normal. We only see this in scans, though. And sometimes we just want a picture. We just want a visualization. And our visualizer does that. But if we do want this quantifiable data, if we want an absorbance that is assigned to these numbers, then we need to use something like these scanners in order to obtain that information. Again, as before, when I make a calibration chart, After the instrument is going to do what it needs to do, that's great. We are going to see an absorbance, and that absorbance is going to go onto the y-axis. And then on the x-axis will be our concentration. We know what standards we've made. We know what we've applied. We know now the absorbances from the densiometer, and we can plot those absorbances from the scanner, aka scanner, onto the graph, and we can build this regression line. So this is the way that we quantify data. We treat it no differently than any of the other instrumentation methods that we have used, that we have operated at this moment. It's just, again, a different new way of quantifying on HPTLC. All right. In the next video, we're going to start the next section of information that's going to show up on the upcoming assignments. And this is going to be calculating retention factors. So we're going to go through a little bit of the math, talk about the things to do, not to do, what to watch out for. And from that moment, we'll get a better feeling of how all of this really wraps up into one type of method that we can call TLC or HPTLC. So we'll maybe finish it out in a couple of more videos. And until then, that's when I'll see you.